Okay,
Mm.
so we're going to go through these questions. So we're on the multiple choice for Unit 3, and the question asks, which particle diagram shown above best represents the strongest intermolecular force between two ethanol molecules? Okay, and so here you can see you've got your O here, you've got your H here, right? So this is a hydrogen bond, whereas this
Right.
is this is two H's interacting with each other. So this is a van der Waals interaction. So
Mhm.
what's going to be stronger here, Caton, the hydrogen bond or the two van der Waals interactions?
Yeah, this is gonna be, the hydrogen bond is gonna be stronger here.
Yep. So diagram two, right
Yeah.
here, okay, because there's a hydrogen bond. Yeah, answer C. All right. Question two. So lithium plus, magnesium 2 plus, sodium cation, and calcium cation. Okay. The diagram above represents four cations all shown to the same scale. Which cation would be predicted by Coulomb's law to have the strongest um, ion dipole attraction to water, and why? Okay, so which one's going to bond most strongly to water, and why would it do that? What do you think?
Okay. So, let me see, I have here selected sodium, and my reasoning for that is because it's got it's, period 3, if I'm not mistaken, and so it's going to have the greatest, um, electron shielding, meaning that its valence electron is going to be the most free to move about and interact. But it's also the closest to noble gas configuration, so that it only has to lose one electron instead of calcium's two.
See, I would go with magnesium here because it's the smallest, and it's got like I said, it has the largest charge to size ratio. So that thing really wants to get surrounded by some negative charge fast. It can't
Okay.
really stabilize its positive charge.
All right.
So I would go with magnesium 2 plus. Let's
Okay.
see
So
which
what
one's
is the?
correct. I'm gonna guess that one, or I'm gonna
All
select that one, and that's correct. Yep.
right. Okay.
So we can go through the explanation here. Yeah, but
Yeah.
that's essentially what we said. Yeah, that's the deal, right? So like this thing's got a 2 plus charge, and it really wants to get stabilized.
Okay.
Yep, it's a small atom, and negative like charged things don't like
Hmm.
to be localized. So better for something big to have a negative charge than for something tiny to have a negative charge, or better for something big to be positively charged than something small to be positively charged. Basically, the bigger the atom, or the bigger the molecule, or the bigger the compound, whatever it is, the chemical, the more readily it can um, stabilize some charge, whether positive or negative.
Okay.
Hmm?
So that's why magnesium here is the least stable and most wants to interact with water.
That's correct. Mhm.
Okay.
Yep. Okay, so this situation. All right, so solid compound of group 1 alkali metal and group 17 halogen dissolved in water. The diagram represents one type of solute present in solution, which identifies a solute particle and best helps explain how the solute particle interacts with water molecules. All right, so what do we, basically the question is, what is this guy? Is this a cation, a metal cation, or is this a non-metal anion? And how do you know based on what the water molecules are doing? That's really what this question is asking.
So I got this as a positive ion, so it'd be a cation. So the metal cation portion here, and my reasoning for that is because water, being a polar molecule, has the oxygen in the water molecule has a partial negative charge because
Yeah.
it's more electronegative than the hydrogen. So it's going to be attracted to something with a positive charge, which is exactly what the metal cation would have.
That's exactly right. So this guy must have a positive charge because we know that in water here, these water molecule these oxygen atoms here have the partial negative charge. Okay, these guys are partially negative here, 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 and here. So they're going to orient themselves toward the positive charge. Very good.
So
Oh, yep, that's right. So what's the answer then?
yeah,
Positive
I got C.
ion dipole interactions. Yeah, that's correct. Yep, you've got an ion here and you've got a dipole here with the water. The dipole looks like this. Yep.
Yeah.
Okay. Yep. All right. So, okay. So next up is this guy, number 4. Okay. Oh, this is fun.
Yeah.
Allotrope and then another allotrope. Okay. Diagrams above represent two allotropes of solid phosphorus. Which of the following correctly identifies the allotrope with the higher melting point and explains why? Okay, so what do you think here, Caton?
All right, so I'm going to say allotrope 2 here because it's got that network of covalent bonds, and that's going to be stronger and require more energy to break than the dispersion forces, the intermolecular forces between the P4 molecules. So that basically selection B.
Yeah, exactly. Whenever you've got these actual covalent bonds holding something together, as
Mhm.
opposed to these are essentially van der Waals interactions or the London dispersion forces, same thing, holding these guys together. Okay, whenever you've got, hey, Symphony, welcome. Whenever you've got actual covalent bonds holding something together, then you're going to have a higher melting point. So that's correct. In this business, this number 2 here, metallic bonding, phosphorus is not a metal, so there's no
Yeah.
metallic bonding involved. So that's just a bogus answer. Mhm. All right. So I'm just going to pause the recording really quickly. All right. So the crystal structure of sodium bromide is represented in the diagram above. Which statement correctly compares crystalline sodium bromide to molten sodium bromide in terms of electrical conductivity? Okay. So go ahead and give it a quick look and then we'll talk about it. All right. So what do we think here? What do we think? What's the correct answer?
All right. So I got D as the correct answer here.
Okay, so you got crystalline sodium bromide contains no freely moving electrons, but molten sodium bromide is composed of freely moving sodium plus and Br minus ions, which allows it to be a good conductor of electricity. Okay, and what did you think, Symphony?
I was in the midst of figuring out between A and D.
Okay. Yeah, I mean, that's interesting, right? So
Yeah.
A is totally true for the first part,
Right.
can flow freely in molten, which is a good, it's not really that the electrons flow freely, but it's got
Mhm.
freely moving ions, which allows it to be a good conductor of electricity. So it's actually D. D is more specific, and that's why D is correct. We'll
Right.
double check that. But
So
yeah.
because those freely moving ions kind of simulate how the sea of electrons would move in like a metallic substance.
Yeah, I mean, freely moving ions are a dead giveaway for something that's conductive. So like if you have regular pure water, that's actually not a conductor. But if you dissolve salt in your water, then
Yeah.
then you've got freely moving ions and the water is electrically conductive. That's true. And I imagine I don't know exactly what the mechanism for that is, but I imagine that like if you start to run electrons into the thing, then like those electrons could be transferred to like positively charged like cations in solution, and they could ultimately be like transferred out of solution. So on the other end, like those positively charged cations that become neutrally charged then release those what is it, those electrons on the other
Hmm.
end.
Okay.
Yeah, 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 that actually, yeah, that makes perfect sense. Yeah, and it's also true that like if you short circuit a solution and you run some electricity through it, you'll actually create like if you run electrical current through sodium chloride, like dissolved in,
Hmm.
anyway, no, that's a good talk on it. If you run electrical current through sodium chloride, you produce sodium metal and chlorine gas. But I don't know if you have to do that through solid sodium chloride or if you do that through the
It's
dissolved species.
it's actually got to be molten. I looked it up. That's how they molten sodium chloride. Yeah, that's how I looked it up. That's how they make sodium metal.
Holy smokes. Okay.
Yeah,
That
because
makes
you do it through water. All you do is electrolyze it.
right. And then it won't really run through the solid stuff. So you have
Right.
to melt it. Right. Wow. Okay. That's cool. So it'll just go through the, okay. Nice. Wow. Okay. That's crazy. They got to heat that stuff up. What's the melting temperature of sodium chloride?
Really high. I can. Yeah.
That's a crazy process. Okay. Hmm. The
Yeah,
water-
just 1500 degrees Fahrenheit.
Oh, okay. That's
That's
crazy.
that. Yeah, it is. That's
Hot.
like close to the melting point of steel.
That's hot. Okay. Yeah, that's really hot. That's like 500 degrees or maybe 700 degrees above what your wood-fired pizza oven operates at. That's crazy.
Yeah.
Okay. That's hot. So that's really hot. All right. So number 6. Okay, so you've got diamond and graphite, two allotropes. Which of the following statements best helps explain why diamond is much harder than graphite? Okay, so give it a quick read and we'll talk about it in about 30 seconds.
Give me like 30 seconds.
30 more seconds? Okay.
Could it be C?
Yep, that's right. Uh-huh. These layers don't have covalent bonds joining them together, but then every single carbon atom here is connected to like 4 other carbon atoms. And so there are no like non-covalent attractions joining layers together. These are all like this whole structure is held together through covalent bonds. Yep. Okay, Kate, you got the same thing?
Yeah.
All right, let's move on. Number 7. So a gaseous air fuel mixture in a sealed car engine cylinder has an initial volume of 600 milliliters at 1 atmosphere. To prepare for ignition of the fuel, a piston moves within the cylinder, reducing the volume of the air fuel mixture to 50 milliliters at a constant temperature. Assuming ideal behavior, what is the new pressure of the air fuel mixture? Okay, so it went from 600 milliliters down to 50 milliliters. Okay, so okay, this is a pretty straightforward problem. Um, let's go ahead and just take a few minutes, like a minute or so to solve it, and then we'll share out. Okay, so Caton's done a really good job of providing a calculus derivation here, right? So like a general approach for looking at this if you're familiar with calculus. If you're not familiar with calculus, then there's a different way to go at it. So Symphony, how would you do this problem? Because I know you're not in calculus yet, so you'll use a different treatment, which is the same treatment I would use.
So I knew that.
Or do you have it? Can you start with a formula?
Oh, PV equals nRT.
PV equals nRT, good, but can you talk about like P1 and V1 versus P2 and V2?
Oh, I didn't use that one, but
Oh, okay. So
okay.
like the easiest way on this one is P1 V1 equals P2 V2, right? And you can get that from PV equals nRT. You can say PV equals nRT, and you can say, well, P1 V1 equals N1 times R times T1, right? But you know that N and T are not going to change. So that same quantity is also equal to P2 V2. And then that's why you can say P1 V1 equals P2 V2. So if you follow that approach, then Symphony, take me through the calculation.
So P1 would be 600 milliliters.
That's
And
that's V1.
P1 would be 1.
Yeah, 1 atmosphere, good.
V1 would be 600 milliliters. And then that would be equal to P2, which would be what we're trying to find.
Yeah,
So,
P2, which we don't know.
and then V2 would be 50 milliliters.
Okay, and then that means P2, if you do the math, you gotta divide both sides by 50, you get P2 equals how many atmospheres?
12.
Yep, 12 atmospheres, okay? And that's answer choice B. All right, any questions? Okay, so there we have it. Okay, let's take a look at number 8. So at 10 degrees Celsius, 20 grams of oxygen gas exert a pressure of 2.1 atmosphere in a rigid 7.0 liter cylinder. Assuming ideal behavior, if the temperature of the gas were raised to 40 degrees Celsius, which statement indicates the new pressure and explains why? Okay, so go ahead and take some time. Very similar problem. Okay, so let's go ahead and head through this one. So, Caton, how did you solve this problem?
Okay. So again, this is kind of another PV NRT problem we get here. Um,
Okay.
Instead, we're looking at, yeah, so again, we're looking at the volume is constant, temperature is constant, mass of
Temperature
gas is
constant?
constant, or wait, oh no, temperature is not constant, excuse me.
Right.
Mass is constant, R is constant,
And volume's
so
constant, right?
volume is constant. So
So
you get,
basically, yeah, in this one you got volume, number of moles, and R, of course, being constant. So you
right,
have P1 over T1
mhm,
equals
P2
U
over
over
T2.
T2, right? Like that's
There you
just the easy, quick way to kind of get this whole thing set up. So you've got that situation, right? And what you're really
Right.
looking for is P2. Okay,
Right.
you're looking for P2 because you've got everything else. So if you rearrange, what do you get, Caton? How do you rearrange that? P2 equals,
So P2 equals P1 times T2 over T1.
yeah, P1, right, times T2 over T1. Okay, and so that's exactly right. And we have to deal with temperature in what unit? Are we dealing with Celsius here? Well, the Celsius is
No,
what's in the problem, but in terms of the PV equals nRT equation, do we use Celsius temperature?
no. So yeah, we're working with the like absolute temperature here. So we're going to be using units Kelvin. So
Exactly.
Kelvin is just Celsius plus 273.
Yep. And so when you do that, you get 2.1 times what is it? 313 over 283.
Yeah. So the only answer that makes sense is B.
Yeah,
Like
B.
you don't even have to do that math because C and A are too low, and then D is just way too high.
Yep. And is that the same thing you got, Symphony?
Yeah.
Perfect. Okay. So I'm going to go ahead and erase this guy. And then let's move to number 9. All right. So 2 sealed, rigid 5-liter containers each contain a gas at the same temperature but at a different pressure, as shown above. Also shown are the results of transferring the entire contents of container 1 to container 2. No gases escaped during the transfer. Assuming ideal behavior, which statement is correct regarding the total pressure of the gases after they are combined? Okay, so same temperature, different pressure. Okay, and then they're combined into the same container. Oh, okay. So this is assessing our understanding of Dalton's law of partial pressures. All right, this should take us maybe a minute to go through. Okay, so we'll pause. All right, so Symphony, why don't you take us through your answer?
So I got A for this answer.
The sum of the initial pressures. Okay.
Yes, because once it said the sum of the initial pressures, that already became like my first answer. But when you read B, it says that the total pressure is lower than the sum, or that it's higher than the sum in C, which doesn't make any sense.
Yeah, there's all this stuff you're ruling out. Very good. Lower, higher doesn't make sense. Cannot be determined doesn't make sense. Good, right? But this one makes sense
Mm-hmm.
according to Dalton's law of partial pressures, right? This
Yeah.
pressure plus this pressure are going to give us 1.8 atmospheres over here. Yep. Okay. Any questions about that?
No, looks good to me.
Perfect. Okay. So then let's take a look at the next problem. All right, diagram 1 and diagram 2. The diagrams above use arrows to represent the speed of a gas particle. Which of the diagrams best represents the speed of the particles of a gas at a fixed temperature and why? Okay, so fixed temperature and why. Okay, so like you'll notice that these guys all have the same length arrow, and then these guys have arrows of different lengths. And these particles are supposed to, these samples are going to be at a fixed temperature. So which one is better? Okay, which one's more realistic? So just off the top of your head, what do you think? What do you think? Which one is more realistic?
So I know we did this one before, and I thought it was number one, and then you said it was number two because in even at like constant speed or even at fixed temperatures, there's variations in the speed.
That's right. Yeah. These guys don't have all, like, they don't all have the same velocity. That's not true. Rather, they have a distribution of velocities, so, or speeds. So this diagram is correct because they're bouncing into each other. So when things bounce into each other, sometimes one particle takes more of the kinetic energy from that collision than another, and so they've got a variety of different kinetic energies, not all the same kinetic energy, but the average is what's constant. Okay, and that's held there by the constant temperature. Okay, so what's the correct answer then? Ah, D. All right, and Symphony, does that make sense?
Yes.
Okay, so D's correct, and we're moving on. All right, so I want to say that's okay. Let's move on. So, oh, I checked. Okay, yeah, that's fine. Thank you. Okay, so number 11. All right, so yeah, and then here, yeah, exactly. So like here's a distribution that shows your percent of molecules with different speeds. And so I want to talk on it. Like, let me just look this up really quickly. I think that's a Boltzmann distribution, but let me make sure that's the right name. Yeah, that's a Boltzmann distribution. Yeah, that's what it is. They don't the gas particle velocities or speeds don't obey a normal distribution or some sort of like constant value. They obey a Boltzmann distribution. Okay, which is it's got some like similarity. It's got this peak here, not too different from a normal distribution, but certainly distinct nonetheless. Okay, so the two gas samples represented in the graph above are at the same temperature. Which of the following statements about the gases is correct? Okay, so, oh, this is interesting. Okay, so you're looking at gas Z versus gas X, okay? And so Z is the dotted line versus X is the solid line. So this is Z and this guy is X, okay? So go ahead and just take a minute or so to look through that problem. All right, so Symphony, what do you think?
I think the answer is B.
B, there are fewer molecules in the sample of gas Z. Okay, because it's sort of like a lower peak here.
Yeah.
That's kind of misleading because like these really like assume that they have the same area under the curve, so that there's the same amount of each. So it's kind of rule that one out. But like, what do you see here? Like if you were to draw, like, what does this tell you? Like if this is if like this is sort of your average, like this is sort of like the middle of the molecules for Z, and then this is sort of like the middle of where the molecules are in X. Which one has the greater average speed?
B.
Z, yeah, and that's correct. So they have average higher kinetic energy. Oh, actually, they might be at the same temperature. So, okay, the gas samples are at the same temperature. Which of the following statements? So they're at the same temperature. They have the same kinetic energy because they're at the same temperature, but that means one of them is moving faster. So if you've got, and you haven't taken physics yet, that's why this problem is tougher. So kinetic energy equals 1/2 mv squared, right? And so they have to have the same kinetic energy, but gas Z, right, has a higher speed. Why? Because it has a lower mass. So gas X is heavier than gas Z. So gas Z has a smaller molar mass than gas X. C, that's the correct answer.
Yeah, I thought it was going to be A just because.
Yeah, but then you realize they're at the same temperature, you got to rule that out.
Okay.
Yeah.
So temperature is the determinant here of kinetic energy.
Yeah. What now?
So temperature is the determinant of kinetic energy with gases.
Yeah, exactly. Uh-huh. With
Okay.
anything, like the average internal kinetic energy of anything at the same temperature as anything else is the same.
Okay.
Yeah. Yep. So yes, that's the deal here. So like because these guys have the same kinetic energy, Z has to be smaller because it's moving faster.
Okay.
Yeah. Because again, like KE equals 1/2 mv squared. Ke equals 1/2 mv squared. Okay, like that. All right. So number 12. Okay, relative number of molecules, speed. Okay, the diagram above shows the distribution of speeds of a sample of O2 gas. Which of the following graphs shows the distribution of speeds for the same sample at a higher temperature, dashed line? Okay, so here you've got whatever temperature, and then you've got a higher temperature. Okay, so one of these is going to represent, the dashed line is going to represent the higher temperature. Okay,
Right.
so which one of these is it going to be, right? So this is just understanding your Boltzmann distribution.
Yeah.
So go ahead and
It's
give
gonna
this.
be C
Go
or
ahead.
D.
And yeah, go ahead and give this a look. Take like 30 seconds, and we'll talk about it. All right, so Symphony, what do you think? Did you get an answer for this one?
I don't know for this one.
Okay, so temperature's going up, right? So
Mhm.
higher temperature. So what's happening is as temperature goes up, is kinetic energy increasing or decreasing?
Mm, decreasing?
No, when temperature increases, kinetic energy increases.
Okay.
Okay, so if kinetic energy increases, then what increases, the mass or the velocity of the sample?
I mean, that's going to be the velocity.
Yeah, you're not adding any mass there, right? So like it's got to start going faster. Okay, so which one of these graphs indicates that the sample is moving faster?
Okay.
What do you
So-
think, Tiffany?
D?
D or C, right? They're both kind of faster, right? So if you look
Mhm.
at C, you've got like the peak for C is to the right of the peak for the original peak, right? So that indicates faster molecules. And then here you've got a faster peak here than over here, right? So okay, and then you got to choose between D and C. All right, and that's the nuanced part. So what do you think, Caden?
Okay. So C looks a lot like what we just had in the last one, where it's got the same total kinetic energy, just distributed differently.
Right.
Whereas D is definitely going to have a higher kinetic energy.
Okay.
So that being said, I feel like as temperature increases, though, the distribution is going to get wider.
Yeah.
That's where you see those fatter tails on either end.
Yep.
So I could make kind of an intuitive argument for either case.
Okay, so here's the giveaway. So we
Uh-huh.
have to know that our Boltzmann distributions always account for some proportion to be at 0.
Okay.
So like this is not a
Oh,
Boltzmann distribution. That's not what we're dealing with here. And so let's think intuitively about why this makes sense.
right.
If you're heating something up, you're going to have a larger proportion at a higher temperature, right? So a larger
Right.
proportion is going to be moving faster. That doesn't mean that there can't still be some really slow moving particles in your sample. There absolutely can be.
Right.
So your whole peak doesn't shift like this. This is artificial. C is correct.
Okay.
Okay.
Cool.
Yeah. And then Symphony, I know this is a little like unintuitive for you. It's just because you haven't seen physics yet. And so like once you've taken physics, like all of this will make sense. And then when you take chemistry again in college, it'll all make sense yet again. Okay, cool. And like getting a good score on the AP test will still give you college credits. So like you'll still have the credits even if you take chemistry again. Like that happened for me. So like it helped me graduate earlier than I otherwise would have. Okay.
Okay.
All right. So number 13. Okay. Equimolar samples of CH4 gas and C2H6 gas are in identical containers at the same temperature. So, okay, so ethane gas deviates much more from ideal behavior than methane gas does. Which of the following best helps explain this deviation? Okay, so there's some deviation from ideality and what's going on. All right, so what do we think, guys?
Okay. So I know that it's not going to be A because they're not hydrogen bonding. That's just not
Good, right? There's no
Right.
hydrogen bonding because there's nothing to polarize the H, right?
right.
So what's our little acronym, our little saying that reminds us what's gonna hydrogen bond?
Hold the phone.
Good. Where phone is spelled how?
Right. FONE. So
F-O-N. Okay, just
FO.
So if there's no fluorine or oxygen or nitrogen bonded to your hydrogen, you're not going to have hydrogen bonding.
Right.
Okay, so this is totally out, right? That's gone. Okay, so what about B? Symphony, what do you think of answer choice B?
B, I eliminated because I don't know. That was just one that I didn't feel like was right.
Okay,
That was
so
between
you eliminated it, right? But let's take a look at it. So let's look at this thing. So C2H6, that's C dash C H H H H H H, right? Is C2H6, is that going to be bigger than CH4 or smaller than CH4? And CH4, of course, looks like this. Which one's bigger?
C2H6.
Yeah, so it is larger, right? And does this chemical have like an electron cloud? Are these electrons here? These bonds, are those made up of electrons?
Yeah. I'm not sure.
You don't know if covalent bonds are made up of electrons?
When it comes to like electrons, I have no idea what happens.
No,
That's like well in chemistry for me. I have no idea.
no. Symphony, covalent bonds are made up of electrons, remember? Like
Mm-hmm.
if you talk about like carbon, right? It's got 1, 2, 3, 4 valence electrons, and
Mm-hmm.
every hydrogen has 1 valence electron. So
Mm-hmm.
they come together like this. Remember us doing all this?
Yeah.
Okay. So like these dots here represent covalent bonds, right? Which are made up of electrons. And so you can draw them like this, or you can draw them like this.
Okay.
Okay. So those are absolutely made up of electrons. So I wouldn't rule out B, but let's take a look at C. C, what do you think of Caton? Caton, what do you think of C?
Okay, this one I know is a trap because it says up there that they're at the same temperature.
Same temperature, right? So
Average
and
kinetic energy is going to
yeah, so they can't have different kinetic energies. And then what about D? What do we think?
be. Yeah, I don't know for D.
Okay, let's think about it, right? So
Right.
Symphony, which one of these is heavier? C2H6 or CH4?
C2H6.
Good. So which one's going to have a greater average speed? Right, they're at the same temperature, so they have the same average kinetic energy, right? So kinetic energy, remember, equals 1/2 mv squared, right? So on average for any given gas particle, right? That's true. Okay. So between the two samples. So what's going on with this? So is like which one's got faster moving particles? The bigger one or the smaller one?
The bigger one?
No, because if you're bigger, right, you've got a bigger mass term, that means your velocity term has to be smaller to compensate for the fact that your mass term is bigger. Okay. And this is what we said earlier on about, it was a different problem. It was like gas Z versus gas X. So it was like, God, which problem was it? This one here, right? We said gas Z had to be smaller or less massive than gas X because it had a greater average speed. So what's going on over here? So this guy is bigger than this guy. So its average speed has to be greater or less than this average speed. What do you think? Yes. Okay. It's bigger. So like if their kinetic energies are bigger, but the mass of this guy is larger, then its velocity has to be smaller to compensate for that. Okay. Very good. So D is correct. So that really only leaves us with B, right? And B ends up being the correct answer because again, like C2H6 is bigger and it does have a more polarizable electron cloud than CH4. Okay. And so that's why like that's why so like if you let's see, boiling point, or butter, right? So like butter will boil. Okay, let's go with olive oil instead. So olive oil, yeah, that's crazy. Okay, so like olive oil burns at 570 degrees Fahrenheit, right? So olive oil consists of triglycerides. So you've got these molecules, right? These oh oh oh, and then with these long like so hydrocarbon chains, these fatty acids, right? Right. And I'm just drawing them disorganized. I'm not indicating double bonds or anything here, but this is your average olive oil molecule, right? And it's got these long hydrocarbon chains at the end. And olive oil has a boiling point of like 570 degrees Fahrenheit, right? Whereas water molecules, right? They're held together by hydrogen bonds. What happened? Okay. Are we still here? Can you guys hear me?
Yeah, I can hear you.
Yeah.
Looks like what in the world happened here? What the heck is this? Looks like something's gone wrong with my Wi-Fi.
I know.
I don't understand.
Just quarantine things.
Let me. What in the world? Let me pause the recording. The water's got these dipole-dipole interactions. So, or hydrogen bonds that hold it together, right? So like this hydrogen can hydrogen bond with um, an oxygen atom from a different water molecule. And so even though water is held together by stronger interactions, right, there aren't as many of those interactions. So those interactions aren't as dense, right? So like these little tiny molecules um, aren't as big as the triglycerides that comprise olive oil. So because olive oil has these big molecules that have these highly polarizable electron clouds, like because they're like big molecules, they hold together more tightly than smaller water molecules hold together. So water has a lower boiling point of like 211 Fahrenheit versus olive oil's boiling point of 570 degrees Fahrenheit. Okay, so looks like we need to stress that. I need to stress that more next year. But for today, does that make sense, or do we have questions about that? Because I want to make sure that I get through that effectively for our purposes today.
Yeah, no, I've got this.
Okay, Symphony, does that help?
Yeah.
Okay, all right. But then Symphony, are you good with electron configurations and bonding, or do you feel like that'd be a good thing for you to go back and review?
I'm good with electron configurations, bonding. Yeah.
Okay, so that I think we reviewed some of that stuff earlier, so that might be Unit 1 or Unit 2. But we'll definitely get to it again. Okay, and we're all in the same boat. We all have different things that we have to review. So let's take a look at number 14. Okay, so CO2 and NH3 can be liquefied at 20 degrees Celsius by compressing them to sufficiently high pressures. A student claims that ammonia can be liquefied at a lower pressure than carbon dioxide can be liquefied. Which of the following is the best justification for this claim? Okay, so, oh, this is really interesting. Yeah. So this is very related to what we were just talking about. Give it some time. Okay, think about it. Okay, so what do we think about this one? Who wants to get us started?
Okay. So I can walk through each of these if you like.
Let's go to the right answer. Let's just get to it. I feel
Okay.
like I want to try to get through as much of this as we can because we've got tomorrow, and so it looks like we'll probably get through half of this today-ish, and then we'll probably have to finish up on Unit 3 tomorrow. So that'd be a nice stopping point before the weekend.
Okay. Yeah. So I think it's going to be A. So the average speed of NH3 molecules is greater than that of CO2 because NH3 have less mass than CO2 molecules have. And
Okay.
That doesn't directly translate, but everything else seems kind of goofy to me. So
Okay.
CO2 is a nonpolar molecule, no significant intermolecular forces. NH3 has strong London dispersion, intermolecular force as well. I don't know how true that is because, you know, the
Well, I
non-hydrogen.
actually got a different answer than A, Caton. So, Symphony, what did you get for your answer?
For this one, I got A too.
A2? Okay. So, the answer for this one, guys, is actually D.
Okay.
Okay. So, D is the correct answer here. And I'll show you why. All right. So, CO2 is held together this way. So, CO2 looks like, and that's a nonpolar molecule, right? Because you've got oxygen, you got one dipole here, you've got another dipole here, right? But it's nonpolar altogether because those dipoles cancel each other out. Whereas in NH3, nitrogen, remember, hold the phone, right? Nitrogen is bonding with hydrogen. So it's sucking electron density away from the hydrogen atoms. So you've got little dipoles here and here and here, all adding up to one big net molecular dipole here. So that molecule is polar, and polar molecules of the same size as nonpolar molecules hold themselves together better, okay, as liquids than the nonpolar molecules do.
Okay.
So that's why D is the correct answer.
All right.
Okay. All right. So let's take a look now at question number 15. Real gas, ideal gas. Okay. So that's really interesting. Okay. So yeah, there are like two different different things that are being illustrated here. So you got your real gas here, and you've got your in black. You've got your ideal gas in what is it? In dashed line. Okay. So the graph above shows how a particular real gas deviates from ideal behavior at very high pressures. Okay. So high pressures, there's a huge deviation here, right? Okay. Based on this information, which of the following is most likely the gas and gives the reason based on kinetic molecular theory? Okay, so give this a shot and we'll talk about it in a minute or so. All right. So, okay. So what do we think, guys? Caton, which answer did you get?
So I got D here.
Okay, and then Symphony, which answer did you get? Oh,
What's D for this one?
which one did you get?
What's D? Like I can.
D. SO2.
For this one, I'm not completely sure.
Okay, that's okay. So I'll take us through this. So basically, one of our ideal gas assumptions is that ideal gases are point masses, right? So an ideal gas is a point mass. Okay, that means, okay, volume equals 0. It has no volume, but it does have mass, right?
Oh, okay.
And so when you decrease the volume for a real gas, at some point you get into a situation at which the gas's real volume becomes a factor. And so it starts bumping into itself, right? Like, so like gas particles start colliding with each other. And at that point, right, you're going to have an earlier increase in pressure, right, over here, right? It starts to really increase, right, or wherever. It's just increasing to the right, okay, farther to the right, then this thing increases, right? So this thing increases sooner than this one because of interparticle collisions, okay? And so the easiest choice is definitely D because it's the biggest, okay? It's going to occupy the largest volume.
Okay.
Okay, and does that make sense, Symphony?
Yeah.
You sure?
Yeah, that makes sense.
Okay, so that's that. So yeah, I mean, like one of the tough things about this unit is that we're getting into a lot of little points all over the place, and they're kind of isolated. You won't have to think about them when you're thinking about, say, like thermodynamics, right? But if you're thinking about thermodynamics, you're going to have to think about stoichiometry. You're going to have to think about bonds. You're going to have to think about temperature, a bunch of other things. But like, you're not necessarily going to be thinking about like this thing here, right? Like, I don't know why you would. So this is stuff that you kind of only see in this unit. Okay, so that's why it's really important to master this unit, because you could see this stuff on the AP test. And there are a bunch of questions on this, so I imagine it'll be weighted reasonably heavily. All right. So, and that also is a really good question, right? Like that's absolutely an AP exam style question. I could see you having to explain your way through something like that on this particular AP test. Okay. So, what volume of 0.1 molar HCl stock solution should be used to prepare 250 milliliters of 0.0250 molar HCl? Okay. So this is a C1V1 equals C2V2 question. All right. So I'm going to pause the recording. Okay. All right, Symphony, are you ready on this one?
Yeah.
Okay, why don't you take us through it?
So for this one, I use C1V1 equals C2V2, and C1 was 0.100, and then V1 was what we're trying to find, and then C2 was 0.0250, and V2 was 250 milliliters.
Right.
Once you calculate that, V1 equals 62.5.
Yeah. Okay, good. And I don't have much board space here, so I'm not showing all the units, et cetera, like I usually do in class, but that ends up being correct. And I've swapped these two. So this is the concentration here. This is the volume over here. Okay, so that's correct. 62.5 milliliters. Is that what you also got, Caden?
Yeah, 62.5.
Perfect. Okay, so I'm going to go over here. A 500 milliliter aqueous solution of sodium phosphate was prepared using 82 grams of the solute. What is the molarity of sodium phosphate in the resulting solution? So 500 milliliters. Okay. Oh, I see. You're using, so it's normally it's got a molar mass of 164 grams per mole, but you're using 82 grams of it. Okay. In 500 milliliters of solution. So what's the molarity of this thing in the resulting solution? Okay. So this is just a molarity calculation. Take 30 seconds. All right. So Caden, take us through this one.
Okay, so all we have here is a half a liter of solute and then half a mole of or half a liter of solvent, half a mole of solute.
Yep.
So
half a liter
right.
and half a mole. Yep. So 1/2 mole per 1/2 liter equals.
So this just, it seems most convenient to me. I like to deal with whole liters anyway, so I was going to double everything anyway. So doing that, you get 1 mole per 1 liter, which is just 1.0 molar.
Molar. Yep, 1 molar. Okay, 1 mole per liter, 1 molar. That's that. Is that what you got, Symphony?
Yes.
Perfect. Okay, and we're out of here. Okay.
All right.
So yeah, one quick thing. So like regarding the polarizable electron cloud and everything, Symphony, like if you're confused about bonding or electrons or whatever, I have to do a better job of teaching it because like you've clearly learned a bunch of material this year and you've done a great job. So that means that like I have to do a better job of like reviewing or teaching in the first place, etc. So that other similarly studious people aren't confused next year. And then we'll of course have time to review because I want everybody to get a really high score on this test. Okay, so how many grams of sodium chloride, molar mass is 58 grams per mole, are needed to prepare 100 milliliters of a 0.25 molar sodium chloride solution? Okay, so, oh, this is fun. All right, so 100 milliliters, 0.25 molar, there's your molar mass. Okay, go ahead and give this a shot. Take a minute or so. All right, so what do we think here? Symphony, do you want to get us started on this one?
Okay. For this one, I got D.
D, very good. Okay, that's what I got. How'd you get that?
So I got D because I just set up the equation 58 over x over 0.1 equals 0.25.
Okay, so 58 divided by x.
Yeah, and then that like one quantity over 0.1.
Oh, I get it. Okay, I see. Okay. So okay. So yeah, I mean, I would probably do this a little differently. So I'll use the method that we used early in the year. So 58 grams per mole. So like basically times 100 milliliters. Is this a C1V1 equals? No. Times Man, that's a funky one to do. So 25 molar, 0.25 molar, 100 milliliters, 0.25 molar. Oh, I see. So I would do it this way. So I would do, okay, so you've got 100 milliliters of this thing, right? So 100 milliliters times 0.25 mole per 1,000 milliliters times 58 grams per mole. And that'll give the same mathematical answer. You're going to get 1.5 grams per mole. Okay. Kate, did you get the same?
Yeah, I got 1.45 grams.
Yeah. Yeah, exactly. That's exactly what I got. Yep. Yep. But we're going to 2 sig figs here, which makes sense because that's what you've got over here. Okay. So any questions?
No, good on that.
Good. Okay. So then let's move on to number 19. Okay. And this will be our last problem of the day. So we'll pick up from here tomorrow. So unit 3, I'll just write that down. Unit 3, number 19. Come on. Unit 3, number 19. Or sorry, number 20 is where we pick up. Okay. All right. So you've got methanol and water. Okay. And we have the molar masses of each and the densities of each and the boiling points of each. Ooh, that's really interesting. Okay. Yeah, okay, that's what I expected. All right. So when methanol and water are mixed together, they form a homogeneous mixture based on the information in the table above. Which of the following would be the best procedure for separating a mixture of methanol and water? Okay, so take a look at what you're given in the table, right? And then try to figure out how you would separate this mixture. All right, go ahead and take. All right, so all right, so I've got the ground screw out behind me. But what do we think, guys, about this one? What do we think our correct answer is here?
Okay, I think this is going to be B.
Distillation, okay? And why do you think that?
Okay, so molar mass and density can't really help us with the given choices here. I mean, all density would be good for like trying to scrape the methanol off the top, but it is homogeneous. But the boiling points are different by almost 40 Kelvin.
Yeah.
So that's a pretty significant difference. So you know that the methanol is all going to boil off before any of the water starts to.
Yeah, there's a difference of 40 Kelvin there. Symphony, did you get the same thing, or what do you think?
I got B.
Huh?
I got B for this one.
B also. Very good. Okay. So yeah, that's the correct answer. Very good job. All right. So that's all for today.